The concept of work is important to scientists and engineers for determining the energy needed to perform various jobs. For instance, it is useful to know the amount of work done when a crane lifts a steel girder, when a spring is compressed, when a rocket is propelled into the air, or when a truck pulls a load along a highway. In general, we say that work is done by a force when it moves an object. If the force applied to the object is constant, this is the definition of work. W equals Ft, where d represents the distance traveled by the object, and F is the applied constant force. Okay, now let's do an example. Find the amount of work done by lifting a 50-pound object 4 feet. So here we have the 50-pound object. And we're going to lift it 4 feet. So we need to use the formula, work equals force times distance. So we have 50 as the force and 4 as the distance. So therefore, work equals 200 foot-pounds. Okay. In the U.S. measurement system, work is typically expressed in foot-pounds, inch-pounds, or foot-tons. In the centimeter-gram second system, the basic unit of force is the dyne, the force required to produce an acceleration of 1 centimeter per second on a mass of 1 gram. In this system, work is typically expressed in dyne per centimeters, or Newton meters, also known as joules, where 1 joule equals 10 to the 7th ergs. In the first example, the force involved is constant. If a variable force is applied to an object, calculus is needed to determine the work done, because the amount of force changes as the object changes position. For instance, the force required to compress a spring increases as the spring is compressed. Suppose that an object is moved along a straight line from x equals a to x equals b by a continuously varying force f of x. Let delta be a partition that divides the interval a to b into n subintervals, determined by a is equal to x of 0, which is less than x of 1, which is less than x of 2, and so on, until x of n, which is equal to b. And let delta xi equal xi minus xi minus 1. For each I, choose c such that xi minus 1 is less than or equal to ci is less than or equal to xi. Then, at ci, the force is given by f of ci. Because f is continuous, you can approximate the work done in moving the object through the ith subinterval by the increment delta wi equals f of ci delta xi. So the total work done as the object moves from A to B is approximated by work approximately equals the sum from I equals 1 to n of delta wi. And using substitution, we could say this equals the sum from I equals 1 to n of f of ci to delta xi. This approximation appears to become better and better as n approaches infinity. Therefore, we define the work to be the integral from a to b of f of x dx. In order to apply this formula, we need to know some basic physics laws. The first law is Hooke's law, developed by Robert Hooke. Hooke's law states that the force F required to compress or stretch a spring is proportional to the distance d that the spring is compressed or stretched from its original length. The formula is F equals kd, where k is the spring constant. The second important law is Newton's law of universal gravitation, developed by Isaac Newton. The law states that the force F of attraction between two particles of masses m1 and m2 is proportional to the square of the distance d between the two particles. The formula is F equals k m1 m2 divided by d squared. Lastly, we have Coulomb's law, developed by Charles Coulomb. The law states that the force between two charges, Q1 and Q2, in a vacuum is proportional to the product of the charges and inversely proportional to the square of the distance d between the two charges. The formula is F equals K Q1 Q2 over d squared. Okay, now let's do an example in which you compress a spring. A force of 750 pounds compresses a spring of 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. By Hooke's law, the force F of x required to compress the spring x units is F of x equals Kx. Using the given data, it follows that F of 3 equals 750 equals K of 3. And thus K equals 250 and F of x equals 250x. To find the increment of work, assume that the force required to compress the spring over a small increment delta x is nearly constant. So the increment of work is delta W equals force multiplied by the distance increment. Which in this example is equal to 250x multiplied by delta x. Because the spring is compressed from x equals 3 to x equals 6 inches less than its natural length, the work required is the integral a to b of f of x dx. And in this example, from 3 to 6, 250x dx, which when you integrate is equal to 125 x squared from 3 to 6, which is equal to 4,500 minus 1,125, which equals 3,375 inch-pounds.
Okay, so now that we've learned about work in Calc 1 and Calc 2, let's learn about work in Calc 3. But first, we have to understand line integrals. Of vector fields. Okay, so the main difference between work in Calc 2 and work in Calc 3 is that work in Calc 3 takes place in 3 dimensions, which is why we have to know line integrals. One of the most important physical applications of line integrals is that of the work done on a particle through a force field, such as a gravitational field or a magnetic field. It is important to mention, however, that the force done through a circular field is constant, while the force along a parabolic curve varies from point to point. To see how a line integral can be used to determine the work done through a force field, let's consider a particle moving along this line, C. However, we only need to consider the part of the force that is acting in the same direction as the particle. We don't need to consider any other direction. This means that on each part of C, you can consider the total projection F dot t of the force vector F and the unit vector t. And now this, along a small sublength arc of delta S, makes the total work, or the work done, equal to force times distance, which is equivalent to force at the point x, y, z, dot the unit tangent vector at the point times the total subarc length. Now this makes the total work done equal to the integral along C of f of x, y, z, dot t, x, y, z, times your delta S I. So now let's let F be a vector field defined along a smooth curve C, where C is given by R of t, where t is in between A and B. The line integral then is then defined as the integral along C of F dot dr, which is equivalent to the integral along C of f dot t ds, just like the example before, and that is finally equal to the integral from a to b of f of xt, yt, zt times, or dot, r prime of t dt. Now, let's do an example. So let's imagine that we have to find the work done by a force field defined by on a particle as it moves along the curve given by from 1, 0, 0 to -1, 0, 3 pi.
Go.
All right, so since RT is equivalent to x of t plus y of t plus z of t, we can infer, or we can rewrite rather, the force field to be equal to -1/2 of the cosine ti plus -1/2 the sine of tj plus 1/4 k. And finally, before we find what the work really is, we have to remember that r prime of t is equal to -sine ti plus cosine tj plus k. Then we can finally use the line integral formula we used before to find the work done by the force field on the particle along the curve C. So now let's go through the work. Get it? So the work is, again, defined along the curve C of f dot dr. When we plug everything in, we get the integral from 0 to 3 pi of -1/2 cosine ti minus the half of sine tj plus 1/4 of k. And then r prime, again, was defined as -sine ti plus the cosine of tj plus k dt. Simplify that down, you get 1/2 sine t cosine t minus 1/2 sine t cosine t, so those cancel out, and you're left with just 1/4 times dt. So again, you get the integral from 0 to 3 pi of 1/4 dt, which eventually simplifies down to 3 pi over 4. So that's the total work done by the force field on the particle traveling along the curve C. So you may notice that x and y were not in this equation anywhere. We only used the z variable changing from 0 to 3 pi. So why is this? Well, it's simply because x and y don't contribute to the total work, because x and y are not along the path that the particle takes. The particle travels along a helic path going upwards. So x and y end up canceling out at every point, and the only variable that's left that's contributing along the same direction as the motion of the particle is the z variable going upwards. All right, so to recap. Work, in its most general definition, is defined by a force applied over a distance d. So now, if there's a changing force, which Rose went over in the first part of the video, you have to break down F and D into different smaller sub-intervals. An important application of work is in Hooke's law and Coulomb's law, and also Newton's law of gravitation, which again was discussed earlier in the video. The most important thing to remember in Calc 3, though, is that since we're now talking about a third dimension, the work done by a force field on a particle is only applied where the force field is in the direction as the motion of the particle. So this means that if you have a force field in the positive y and positive x direction, but the particle is moving in the positive z direction, that means no work is done by that force field on the particle, since the force field is not in the same direction or the opposite direction of the motion of the particle. And that pretty much wraps up work in all of calculus from Calc 1 all the way to Calc 3.